everybody. Today is Science Friday 45, and I asked my dad a question.
Let's get down to it. Well, everybody, welcome back to Science Friday, this week number 45. And I'm joined this week by my son, MJ here, who is a student at Gem Prep here in Pocatello. It's a charter school. They have a really good science program. And he came home a week or so ago, and he had a question for me. What was the question, buddy?
It was, will the sun explode?
Will the sun explode, right? What's going to happen at the end of the sun's life? So I thought it'd be a great Science Friday. It's a good question. And the answer is our sun will not explode, but what will happen to it is equally fascinating. The sun doesn't have enough mass to explode, to become a supernova, as many of you would probably be aware, happens to some stars. So let's talk about the life cycle of the sun this week. And we're going to talk about it from birth to death. So our sun is about 4.5 billion years old. And it started out about 4.6 billion years ago as something called a nebula. And a nebula is just a big cloud of dust and gas floating through space. And this cloud would have been way bigger than the current solar system. It would have been somewhere on the order, several orders of magnitude greater than the current size of the solar system. So this big cloud, this nebula of dust and gas floating through space, encounters a shock wave of some kind. It could have been a nova. It could have been another star exploding. It could have been moving through a slightly denser region of the galaxy. But something causes this cloud to start to collapse more quickly than it would have just under the influence of gravity all by itself. So this cloud starts to collapse, and as it starts to collapse, it conserves angular momentum by starting to spin a little bit more rapidly. Everything in space spins or rotates in some way. So as this cloud starts to collapse, its rate of spin starts to increase a little bit. And the gas that's in it, which is overwhelmingly hydrogen, hydrogen is the most abundant element in the entire universe, begins to form a ball in the center of this cloud. Well, as most of you know, whenever you compress a gas, it heats up. So this hydrogen, mostly hydrogen and some helium, in the center of this cloud starts to compress due to the influence of gravity starting to squeeze all these things together. It starts to heat up. And it forms something known as a protoplanetary disk. So you have this ball of gas in the center, hydrogen and helium, surrounded by a bunch of dust and icy particles that have kind of settled down into a protoplanetary plane. Now, the reason why this stuff farther out settles into sort of a disk instead of a cloud is a little bit complex, but again, the real answer is conservation of angular momentum. So you get this ball in the center, big cloud of mostly hydrogen and helium, and you get this surrounding disk, which is also spinning, and it's mostly dust, icy particles, things like that. As this protoplanetary disk sort of settles in, the gas in the center starts to really heat up, and something known as a protostar starts to form. Now, a protostar is just a hot ball of gas, okay? And it doesn't emit very much light in the visible portion of the electromagnetic spectrum. There's strong infrared signatures because it's pretty hot, but it doesn't emit a bunch of visible light. So our sun spent about 100,000 years in its protostar stage. And as a protostar, the heat is coming from principally two sources. The first source is the compression of the mostly hydrogen gas. The second is the infall. There's a lot of material that continues to fall into the center of this cloud just because it's the center of gravity of this very system. There are some more complex things like some shock waves and things that occur, but that's beyond the realm of what we want to discuss here. So just suffice it to say this protostar gets hotter and hotter and hotter. And at some point, it transforms into something known as a T Tauri type of star. Now, T Tauri stars are wildly energetic. They have these big jets that are associated with them. They're starting to blast a lot of material out in space, but there's still some infall that's occurring. So protostar to T Tauri star is kind of an evolution, sort of the same thing, because it's still not fusing hydrogen into helium in its core. These stars are still heated by just sort of gravitational pressure, squeezing of that hydrogen gas, and then infall of material from farther out in the protoplanetary disk, principally gases. Well, at some point, this T Tauri star gains enough mass that it can compress the center of itself enough that it actually ignites. And ignition occurs when that star's principal source of heat and energy becomes the fusion of hydrogen into helium via something known as the proton-proton cycle. Now, I don't want to talk about the proton-proton cycle in any kind of a detail here because, again, it's more complex than we need to get into. But at that moment, when that protostar, that T-Tauri star, ignites, and its principal heat source is the conversion of hydrogen into helium via nuclear fusion and a process known as the proton-proton cycle, it enters something called the main sequence. And everything that leads up to this is relatively fast compared to the main sequence lifetime. Once a star enters the main sequence, that's the longest phase of its life. And stars like our sun can remain on the main sequence for 10, 12 billion years. It's a really long amount of time, and they're remarkably stable. Their properties don't change very much while they're on the main sequence. Now, we talked about the main sequence a few weeks ago when we were talking about measuring the properties of stars. We talked about something called the Hertzsprung-Russell diagram, and I have one of those up here. And you can see that the main sequence is a big area on the Hertzsprung-Russell diagram, and that's where a star is going to spend most of its lifetime. What happens in the beginning is relatively short, and what happens at the end is relatively short compared to the main sequence lifetime. So our sun is about 4.6 billion years old, and it's been on the main sequence for 4.5 plus billion years. So when a star is on the main sequence, the definition of a main sequence star is that its principal source of energy is fusing hydrogen into helium in its core. Well, this doesn't last forever. And to address MJ's question, what happens when a star reaches the end of its life and what causes it to reach the end of its life? Even though the sun is in the middle of its lifetime right now, we're about halfway through that 10 billion years at about 4.5 billion years. There are some changes that are going to occur in the sun before the very end that are going to make the sun a little bit different than it is right now. As the sun progresses through its lifetime, it starts to use up the hydrogen that it has available in the core. The sun can really only easily burn the hydrogen that's in the very center of the star, the core of the star. The hydrogen that's in the surrounding layers is largely unavailable to burn until the very end, and we'll get into that in just a second. So as that hydrogen starts to run out, it's a little counterintuitive, but the reaction starts to increase a little bit as it becomes harder to scavenge hydrogen. And what that means is that the sun will gradually get hotter because the core becomes more energetic over time. And currently that rate is about a 1% increase in luminosity every 100 million years. Now, 100 million years isn't a long time in the lifetime of a 10 billion year star, which means that it can get quite a bit hotter over time. So in a billion years from now, the sun's going to be about 10% brighter than it is right now. And in about 3.5 billion years, the sun's going to be 40% brighter than it is right now. Its luminosity will increase quite a bit. At that point, all the oceans will have boiled away on Earth, and the Earth just won't be habitable anymore. So well before the sun actually reaches the end, we won't be able to live on Earth anymore just because the oceans will have all boiled away and all the water vapor will have boiled out of the atmosphere. It will be a version of Venus, what Venus is right now, or a really hot Mars. You could think of it either way. Well, so that's what MJ here was worried about. It's nothing to worry about unless you are planning on living to a ripe old age of 3.5 billion years, or a billion years at the lower end of the limit when trouble really starts. By the way, there is no connection right now between the current climate change, the global warming that we're seeing, and power output from the sun. There's no correlation between those two. The time scale's too short and it's way off. So what happens when the sun actually does reach the end of its lifetime? Well, at the very end, when the sun starts to really have a difficult time finding enough hydrogen in its core to fuse into helium to maintain the pressure that's kept the core stable all those years, the core will start to collapse a little bit. So the reaction slows down, the core collapses a little bit, and as it collapses, it gets hotter, and the outer parts of the star start to swell a little bit. And then they start to swell a lot, and it swells into something known as a red giant. Now, the red giant will be 100 times bigger than the current sun, and in fact, the photosphere, the surface of the red giant, will extend out to approximately the orbit of the Earth around the sun. So it'll engulf most of all the inner rocky planets and turn them into cinders, which will be orbiting either inside the photosphere or inside the atmosphere. So this red giant star maintains its energy for about 100 million years or so by actually scavenging some hydrogen that's right around the old core of the star. It's something called a shell source. And it'll fuse that hydrogen for about 100 million years. But at some point that runs out because this reaction is pretty fast to maintain this big star. At that point, the star will start to collapse. And there's something called a helium flash that occurs right at that point. And the helium flash means that for a brief amount of time, the star is actually able to fuse helium into carbon. It's a point called the helium flash. You don't see it from the outside because it's buried well within the star. But the helium flash signals the end of the red giant phase of the sun. So the sun will collapse into something called a yellow giant. Now, the yellow giant is hotter because the star's collapsed a little bit. The core is pretty energetic. It's fusing helium, and that's a much hotter reaction, but it's also a quicker reaction. So the lifetime of the yellow giant star isn't very long. The other interesting thing about the star at this point is the material in the core doesn't obey normal thermodynamic properties. It's something known as degenerate material. Now, not degenerate like you go look at naughty magazines and movies and stuff. Degenerate in just that it doesn't obey the normal laws of thermodynamics. So in many cases, this yellow star is a yellow pulsing star. It will change its luminosity and size a little bit due to the effects of degeneracy in the inside of the thing. Now, about 100 million years is all the sun's got in its yellow giant phase. And at the end of this, the sun will start to collapse again. But stars like the sun just don't have enough mass to be able to use gravity to squeeze carbon into heavier elements. So when the sun runs out of helium, that's the end of the line. It can't do anything else. And what happens is the collapse is relatively gentle. So you don't get a big, gigantic explosion. You get a relatively gentle collapse. And then you get all of this material, mostly carbon and silicon flakes, that expand away from now the exposed core of a dying star, and that forms something known as a planetary nebula. And I've got some pictures of those up here. What's left is the exposed core of a dying star eventually becomes something known as a white dwarf. And a white dwarf is a very, very hot, but not very luminous object just because it's tiny. The white dwarf that will be left over from our sun is going to be about the size of the Earth, so they're very difficult to image at any kind of a great distance. You can see that they're there, but they're very difficult to see optically because they're very small. You're trying to look for an Earth-sized object in stars that are many, many light years away. You're not going to see very many. But you can infer their existence from their gravitational interactions with things around them and some other energy that they produce throughout the electromagnetic spectrum. So that's it. That's the end of our sun. It's not a bang, but a whimper. So our sun will not explode. It won't go supernova, but it will swell into a red giant. It'll shrink down into a yellow giant. It'll expand into a red giant one last time, very briefly, before it becomes a white dwarf star. And that's the fate of our sun. Doesn't blow up, sun, so I'm sorry to disappoint you, but no spectacular supernova. So that's it for Science Friday this week. Thanks for joining me, MJ. And by the way, MJ's insisting we don't paywall this because he wants his buddies to be able to see it. So second week in a row, no paywall on this one. I'll be back next week. Be seeing you. Cheers. All right.